On behalf of 24HourAnswers.com, I welcome you to today's lesson. In this video, we're going to look at an example where we need to find the derivative, and the product rule and quotient rule are going to have to be used together to figure out this derivative. Here's our example: y equals e to the x times x squared all over the sine of x. So we have a product here, and we also have a quotient. And what we want to do is separate this thing somehow, and there's more than one way to do this, but I'm just going to separate it like this. I'm going to write e to the x over sine of x times x squared. This is an equivalent equation or expression because if we multiply all this stuff back together, putting that over 1, we will have e to the x times x squared, which is what we have in our numerator, and sine of x times 1 is just sine of x. So it's the exact same thing, but now I have broken it up into a quotient of a single function over a single function, and then we're multiplying by a single function. Whereas over here we had a function times a function divided by a function, we're breaking it up into pieces that we can work with individually. Now, what I'm also going to go ahead and do is we see this quotient right here, and we're going to, if we call this entire thing right here, we call this f, and we call this thing right here g. Now, if we're trying to find y prime according to the instructions, we have to use the product rule because we have a product of two functions, f and g. So therefore, y prime is going to be equal to f times g prime plus g times f prime. Notice here, if we go ahead and start working this out now, we have y prime is equal to f. We just take f and leave it alone. So we have e to the x over sine of x times g prime, so the derivative of this g is going to be 2x, plus g, now we leave the g function alone, that's x squared, and then we multiply by f prime. So we have to find the derivative of this. So what I'm going to do, I'm just going to come over here to the side, and I'm just going to write f prime is equal to, because that's the part that we are on in our product rule. However, since f is e to the x over sine of x, we have to apply the quotient rule to find f prime. So the way I remember quotient rule is the following: low d high minus high d low all over low low. And if you've seen the quotient rule videos that I've done, it's just a way to remember we take the lower function, so we're finding the derivative of f, take our bottom piece, sine of x. D high means the derivative of the top. Well, the derivative of the top in f is just e to the x, because the derivative of e to the x is e to the x. Minus high, we leave our top function alone. Well, that's going to be e to the x. D low, now we take the derivative of sine, which is going to be cosine of x. And this is all over low low. So we take that bottom function. Low low means low times low. Sine of x times sine of x is sine squared of x. So this is our f prime that we're going to come back and plug in over here into this spot. All of this stuff can be simplified, and I'll just worry about doing that in a second. Let's just take all of this stuff, which is f prime, that's what we're trying to find, and we're going to put it right over here. So here that is, and let's just recap and make sure everything makes sense again. Back at the beginning we had we rewrote it as e to the x over sine of x, which is that part, and then we multiply by x squared. We called this stuff f and this stuff here g. Applying our product rule, since we are multiplying two functions, we take the f function, which we left alone, that's exactly what you see here, times g prime. G prime is 2x because we took the derivative of this. Then we have a plus in our product rule, and then we leave g alone. That's that x squared that you see right here. And then we have the f prime, and that's what we went over here on the green piece, and we did it all over here to the side, and that's what we're multiplying by here. Now we are ready to try to simplify this. This is the derivative technically, but we could simplify this, and I'm just going to spend a little bit of time showing you how you could go about simplifying this expression. So first of all, I'm going to rewrite this as y prime equals, we can bring the 2x and the e to the x together into one piece, all over sine of x. We're just multiplying all that stuff together there. And then this part here, technically we can grow that fraction bar right on across. That's pretty much what I did here when I wrote it down here. And since I did that, what I want you to notice here is we're going to have a bunch of stuff up top, and we can almost combine these two big fractions together. if we had another sine of x down here at the bottom. Notice we got sine squared over here. We need another sine here. So if I come down here and multiply by another sine in this first fraction, that will be a sine squared, and that's totally fine as long as we multiply by another sine of x at the top. So what I've done here really is I'm still focusing on this first fraction. I noticed to get a common denominator between these two big fractions, we needed another sine on this one. So I multiply by sine at the bottom. As long as we multiply this top stuff by sine of x, we're totally fine. And now that we have this, we can actually combine all of this stuff together, this stuff here, and we can put this all over a single sine squared of x because we now have common denominators. That looks a little something like this. So we've taken that sine of x, we've multiplied these top pieces by sine of x so that we get that extra sine of x at the bottom, and that's what we have here. And then I just took this stuff, I added it on since we had a plus in between here, and that's that same stuff that you see up here. And since we have a common denominator, we can put this all over sine squared of x. Now, why would you want to keep doing this? Why are we going to continue on with this? Well, very soon in your calculus course, if you haven't already, you're going to start setting a derivative equal to 0 or some other number. And when we start solving equations where they're equal to 0, it's a good idea to simplify and factor to help you set that equation equal to 0 and give you a better chance of solving it. With that said, I do want to show you one thing. Notice this stuff up here at the top. We got three pieces, or three big old terms is what I call them. We got this piece here, and this piece here, because they're separated by pluses and minuses. So think of these as three big old terms, and if you look at these three terms, they all have an e to the x in it. So think of that as a common factor, a greatest common factor. Let's factor that e to the x out. We're left with 2x sine of x plus x squared sine of x minus cosine of x. Now, unfortunately for this particular example, there is nothing else that we can do with this, but sometimes when you factor out a GCF, you may end up having something in here that will factor out, or factor like a trinomial or something like that. But in this case, we don't. We can't pull out a sine of x because this term here does not have a sine of x in it. We can't pull out an x, even though this piece here and this piece here have an x in it. This one does not. So this is as simplified as we're going to be able to get this one. And if you're taking a Calculus 1 course and you're doing a problem in a textbook and you flip to the back of the book, sometimes your derivative, especially when you start combining multiple differentiation rules, it may not look the same. What you have on your paper may look different than the back of the book. That does not mean it's wrong. What I would encourage you to do, if you think you've got everything right, is try to take your answer, like this initial answer that we got up here, and maybe the answer in the back of the book looks something like this. Using algebra skills and getting common denominators and factoring GCFs may lead or may take your answer that you have on paper and it may match what you have in the back of the book. A very common thing that I see in calculus textbooks is that the answer in the back may not match yours, but they're both correct. It's just a matter of simplifying and trying to make it match up. And there you have it, an example of where we use the product and quotient rule together, a nasty looking derivative, but if we look at getting common denominators and maybe factoring out a GCF, it doesn't look as bad maybe as what it did up here. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.